Okay, so today we'll continue on in chapter 4. You guys have a quiz tomorrow in discussion section, so that quiz will cover up through chapter 3. Okay, so it will not cover the material from chapter 4. It will not cover today's stuff, but you will obviously need to know chapter 4. So this is lecture 4, week 3, Monday. Okay, so this is, we left off on Friday and we said, when describing a relationship, between two numeric variables, there are three things that we want to mention. Okay, and what were those three things that we should talk about? We said one was the shape. And as far as shape goes, we can have linear or nonlinear. We can talk about the direction. The direction can be positive, negative, or neither. And the last thing we want to talk about is the strength. Okay, and we said this can be strong or weak or something in between, moderate maybe. Okay, and so so we talked about the shape, we talked about the direction, and so let's talk about the strength of a relationship. Okay, so as far as strength goes, strength of a relationship. Okay, if it is strong, if the relationship is strong, then that means if we are given one variable, we can make good predictions about the other variable. Okay, so given the value of one variable, we can make fairly accurate predictions of the other variable. Or another way to think of it is we can say there is little scatter around a trend line. And on the other hand, if we have a weak relationship, then, given the value of one variable, our predictions, we can make predictions, but they're just not going to be as good. We'll say will not be expected to be good, to be precise. Okay, or we can say there is, lots of scatter around a trend line. Okay, so let me just kind of illustrate this. If we might have some plot that looks like this, right? And so if I give you, if this is x and this is y, and I give you this value of x, and I say, okay, given this value of x, make predictions for y, your predictions for y would be inside this this small window here. You'd make a small window for your predictions of y. On the other hand, if we have more scatter, okay, and so, you know, there's still kind of an overall general positive trend here. So this, I'm sorry, so over here we would say strong, and over here we would say weak. For this one, if I give you an x and if I give you a y, and I say, here's my x, you know, kind of your predictions for x, for y would be, you know, the window is much wider, right? Much wider prediction window. Okay. This is a kind of a small prediction window for a particular x. Okay, so this is the concept of strong versus weak as far as the strength of a relationship. All right, and so just like before, where we talked about the existence of the IQR and the standard deviation, that those are summary statistics that quantify concepts like spread, we have a summary statistic that will quantify the strength, okay? And it actually quantifies both the strength and direction of a relationship. So this summary statistic is correlation. So the correlation or the full name is the correlation coefficient. Is a number that quantifies the direction and strength of a relationship between two numeric variables. The symbol is R, kind of like relationship. And the interpretation of the correlation only makes sense if the relationship is linear. Okay. Technically, you can calculate correlation. It's just a formula that you just throw your numbers into. Correlation can be calculated for any two numeric variables, but it only makes sense if the correlation, if the relationship is linear. Okay, so technically, correlation can be calculated for any two numeric variables but it only makes sense if the relationship is linear. Okay, and how do we decide if a relationship is linear? What do we have to do? We have to plot it, right? We have to create a graph, and then we look at the graph, and we decide if it looks linear or not. Okay, so to decide, we must plot it, and look. Okay, so just seeing the value of correlation will not tell you if the relationship is linear or not. You can't just look and say, oh, the R is equal to this number, therefore it's linear. R doesn't tell you that. Okay, R can be any value between -1 and 1. So we'll say -1 is less than R is less than equal to 1. Okay, so R can be any value between 1 and -1 inclusive. The sign of R is the direction of the relationship. Okay, so if R is positive, the direction is positive, etc. Okay, if R is negative, the direction is negative. Okay, if R is close to 0, the relationship is weak. Okay. So this, basically something around, if R is less than 0.4, I would say it's weak. Okay. And if R is far from 0, maybe I'll write absolute value R. Okay, if R is far from 0, so that means near 1 or near -1, the relationship is strong. Okay, so we would say, I would say kind of roughly if R is over 0.9, okay, that would be strong. Meaning R is greater than 0.9 or negative R is less than, or R is less than -0.9, right? The absolute value R. But again, to decide if a relationship is linear, you have to make a plot and look at it. R itself will not tell you if the relationship is linear. Okay, so the sign of R is the direction of the relationship, and if R is close to 1, it's strong. If R is far from 1, if R is close to 0, the relationship is weak. Okay, so let's take a look at maybe a few examples. Okay, so we have something. Okay, dots in a perfect straight line. In this case, r is equal to positive 1. Okay. You have a little bit of scatter. Okay. I'm just eyeballing this, but I would guess r is something like 0.95. A little bit of scatter, strong relationship. And you can have more and more scatter. I would guess r something around here to be, 0.65 or something. I don't know. I'm just making up these numbers, so don't hold me to this. Okay. And then as the just the cloud gets more and more spread out, more and more scatter. So, we might still have a positive relationship here. This might be r is 0.3. I don't know, I'm making that up. Okay. Until you get to a point where there's no relationship at all. And so here r would be 0. Now if you make all of these point in the other direction, you'd have negative values, right? So if I have something like this, what would r be here? Negative 0.9 something, right? Yeah, I'm just making up a number here. Okay. Okay. So we have that. Let me draw a few plots here, and we'll get a quicker question here. Okay. So let's say, so right here, okay, so here I have r is equal to 1. So all of these, the dots are supposed to be perfectly on the line. Okay, here I have r is equal to negative 1. Okay. What do I have r? R here would be equal to r here is equal to what? 0. Okay. All right, and then so for your last one, I'm gonna put a little plot here. Okay, and then your options are r is equal to negative 1, b r is close to, but not quite negative 1. So something like r is around negative 0.9. C will be r is around negative 0.5, and D will be we cannot answer. Okay, so for this one, let's do I gotta get the have to get the clicker software started in a second here. Okay. Okay, they're all on this. Okay, so let me get the clicker started. You can discuss with your friends. Sorry. Okay, we'll get. Okay, the clicker box is running here. Okay. All right, and all of the plots, the okay. Discuss with your neighbors. I will go ahead and I'm gonna stop the poll here. All right, let's see. Ooh, okay. All right. The answer is A. R is equal to -1. Okay, so what's going on here? All right. Well, let's just flip back to how we defined R. Okay. The sign of R is the direction of the relationship. So you guys established that it is in the negative direction, so we have a -1. Okay. If R is close to 0, the relationship is weak. If R is far from 0 or near 1 or -1, then the relationship is strong. Okay. And so as far as the strength of a relationship, the strength of the relationship is given the value of 1, how well of a prediction can we make about the other? Okay, how well of a prediction can we make about the other? So over here, if I give you a particular value x right here, if I say x is right here, make a prediction for y, you can make a very precise estimate of what y will be. Okay, there's no scatter here. There's no scatter around the plot, so the correlation is -1. Okay, there's no scatter. So in this plot, so the strength is very strong. Okay, or is actually perfectly strong. And so this is an important thing. Correlation says nothing about the slope. Okay, correlation tells us only about, does not tell us about slope. Only direction and strength. Okay, so if we were to plot all of these, like if you imagine a line kind of like rotating, okay, if it's pointing up in that direction, then it's going to be if all the line dots are in a row, okay, perfectly lined up, all of these have correlation, +1, +1, +1, +1, +1, and then when it's flat, there's no relationship between x and y, so it suddenly becomes 0. And then as soon as there's a tiny bit of downward slope, then it becomes -1. The correlation becomes -1. So it doesn't, the slope doesn't have anything to do with it. It's just, you know, how much scatter there is. And if they're all in a perfect line, then there's no scatter. You're going to have r is either +1 or -1, depending on whether there's a positive or a negative relationship. Okay, is that all right? Okay, here are a few key points. Key points about R, okay? So number one, R only makes sense if the relationship is linear. And that means you must make a scatter plot to decide if it is linear. Okay. The order of variables does not affect R. So that means the correlation, you know, okay, I'll say if the correlation between x and y is equal to 0.65, then the correlation between y and x is also 0.65. If you multiply all of the values for one of the variables, if you multiply all of the values by a constant or add a constant to all of the values for a variable by a constant, or add a constant to all values, the correlation does not change. Okay, so you can, in a practical sense, this means changing your units of measure will not affect correlation. So generally changing from like feet to inches or some kind of units of measure is usually just adding or multiplying by a constant. Okay, so changing the units of measure does not affect R. Okay, and in fact, R itself is unitless. So if you have, you know, the height, the correlation between someone's height measured in inches and their weight in pounds, if that's, you know, has a correlation of 0.6, and then somebody decides to measure height in centimeters instead of inches, then the correlation will still be 0.6. You're looking at the same data. Okay. R is affected greatly by outliers. Okay. Okay, R is affected greatly by outliers. So when you create your plot and you notice outliers, it's a good idea always to investigate outliers. Okay. is there a reason why this one dot is way out here or somewhere else? Doesn't quite fit the rest of the pattern? It's a good idea to look into that. It could be explained away. It could be, somebody had entered the data in wrong. It was a typo, and in that case, you would get rid of it. But there could also be some kind of real phenomena where for certain values you get something unusual. Okay, and in those cases, you may or may want to do a separate analysis where you remove the outliers. Okay, it's a good idea to investigate outliers. Okay, we may possibly want to do a second analysis. With outliers removed. Okay, and then another thing is that the existence of correlation does not mean causation. So you might find that y tends to increase as x increases, but that doesn't necessarily mean that increasing x will cause an increase in y. It could. There could be a relationship of cause and effect, but correlation itself cannot tell you this. Okay, it requires knowledge of the context of the data or where this data is coming from. It requires a deeper understanding. It could point us in the right direction. It could say, well, here are some interesting relationships that we should explore, and whatnot. Okay. All right. Is this all good? Okay. Let's try another clicker question here. Okay. So let's say you have gathered some data. Okay, and two numeric variables. Okay, and you do a calculation. You find the correlation between x and y to equal negative 0.95. Okay, so we will say A is true or B is false. Okay, true or false? So this means that the relationship between x and y is negative, strong, and linear. Okay, so we'll get this started. Okay, and you can discuss with your neighbors. Okay. So this is negative 0.95. This means that the relationship between x and y is negative, strong, and linear. All right, let's take a look. Oh man! All right. Okay. Well, all right. Well, let's. Somebody clicked C. Yeah. Okay. That's like voting third party here. Okay. All right. Well, let's go through and talk about this. Okay. No, I'll just tell you the answer. Okay. The answer is B. It's false. Okay. All right. So this part linear. This is not necessarily true. Okay. Okay. We cannot tell. Correlation by itself will not tell you if it is linear or not. So this is a key thing. All right. Correlation alone will not tell you if the relationship is linear. Right? How do we tell if a relationship is linear? What's the first thing we have to do? We must plot it, right? We must always plot first. All right. And you can definitely expect to see questions like this on, not on the quiz. The quiz only covers chapters 1 through 3, but on the midterm you can expect to see a question where I have not explicitly stated a linear relationship. So you can't assume that, right? So we must always plot first. So if, if we just punched something in, if we have data like this, okay, this is not a linear relationship, okay, not linear. But, R is going to equal something around negative 0.95, okay? So not linear, but R is just a formula. You can punch numbers in, and it will look like this, yes?
But if it's negative 1 or 1, we can say it's linear without?
Yes. If in the exception where R is equal to negative 1 or R is equal to 1 exactly, then you can say there's a linear relationship. But if it's not like that, if it's R is 0.99, you still can't say it's linear, okay? Only if R is exactly equal to 1 or negative 1, okay? So this is not linear, so that doesn't work, okay? Yeah, if you have something like this, sure, you can say R is, the relationship is negative, strong, and linear, okay? R here would be negative 0.95, but this is not linear. So you can't assume that a relationship is linear just based on the R alone. Okay? R can be calculated for any data set, really, any two numeric variables. But again, the relationship, the interpretation only makes sense if the relationship is linear. So I'm going to, calculated any two numeric variables. And let me just also say, we will not learn how to calculate R by hand. Okay? We just have computers do it for us. And I think it's fine, right? Does anyone know how to find a square root by hand? No, right? Is your life worse off because of that fact? No, it's fine, okay? We say, what's the square root of 7? You just give it to the calculator. It gives you a number, okay? Calculating R by hand, it's okay. We're not going to learn how to do it. We'll be fine. But, let me just kind of draw this. So this is a scenario where R would equal 0, okay? But is there a relationship between X and Y? Okay, yes, there definitely is. But there is definitely a relationship between X and Y. Okay, it's a nonlinear relationship then. So again, the interpretation of R only makes sense if there's a linear relationship. There's a nonlinear relationship. Okay, on the other, yeah, and you know, if we have data that looks like this, okay, we'd probably get r is equal to something like 0.8, okay? But again, you know, the interpretation does not make sense because the relationship is not linear. Okay, let me show you, let me take a page out of our textbook. Okay, and these 4 plots, these are called Anscombe's quartet. Okay, all 4 plots have the same correlation, okay? So all plots have r equal to 0.817. However, the correlation really only makes sense for this plot, okay? So r equal to 0.817 only makes sense here. Okay, here's a linear relationship. Okay. Over here, basically, we've gathered data only where x is equal to 8. Okay, so here, you know, we gathered data only where x equals 8. Okay, but we have one point, one outlier. We have one outlier out here, and this is the only point that establishes kind of the correlation. But one outlier, you know, establishes the correlation. And you know, that does not make sense, okay? Or this is a bad idea to do something like this, okay? Let's say, for example, let's say you surveyed 50 people and you said, how much money do you make? How many fingers do you have? Okay, and you get all sorts of answers for how much money people make, right? But then you ask how many fingers do you have, and all 50 people say I have 10 fingers. Okay. And so in that case, it would be kind of like this. Your X is 10 for everybody, but you know, you have different amounts of income coming in, right? Let's say you come across somebody with 11 fingers. Okay, somebody has 11 fingers, and this person, you know, is making $10 million a year or something like that. Okay. And then so if you try to establish a relationship between the number of fingers and income, just that one person out there suddenly shows you, oh, the more fingers you have, the more money you're going to make. Okay, or something ridiculous like that, right? Don't do that. Correlation in that regard doesn't make sense. Okay, right here, we have a similar but different problem. It seems like all of our data line up perfectly along this line. Okay, but we have one data point right here. Okay, and so what's going on here is you should investigate this point. Investigate this point. This is an outlier and it's throwing it off. Okay, if they were all on the line, R should probably be 1. Okay, R would be 1 if the outlier was not here. If the outlier was removed. So the question is, should we keep it? Should we get rid of it? Well, we can't answer that just by looking at the plot. You've got to investigate it, right? You go through, if it looks like it's a typo, sure, get rid of it, okay? But what you probably need to do is you probably want to gather more data around this point, 12.5, 13 or whatever. And if you repeatedly get values here, then you've got some kind of interesting phenomenon, okay? Something interesting where everywhere else, it all, as x increases, y tends to increase, okay? But maybe, could be a typo, could be real phenomena. Hang on a second. And then the last one, nonlinear, so R does not make sense. All right, so these are all things about correlation. In these plots, correlation only makes sense for this one. All right, we'll see you guys on Wednesday.